So I wanted to do a really quick video on key examples of maps. So this would correspond to section 6, some of section 6 in Cambridge Part 2 Dynamical Systems. So yeah, I think the reason I'm doing this first before, defining rigorously what a map is and looking at features of maps is because I think looking at the examples actually helps you to see, to have an intuitive understanding of what a map is, what happens, and how to find out what things map to by looking at a diagram like this. So we'll start with the logistic map, which is defined as follows. So it's a recursive relationship with xn plus 1 equal to f of xn, which is f being the map acting on xn, the previous iteration. And that is defined to be equal to mu times xn times 1 minus xn, where usually we choose mu to be between 0 and 4 so that we don't leave the interval, the closed interval 0, 1. And we also have, x in this closed interval that we do not leave. Sorry, I'm a bit ill today. So if we plot xn against xn plus 1, we're basically plotting the map f. And it looks like this. It's a parabola. And to find fixed points, we simply look at the values on this parabola where, xn plus 1, the next iterate, is equal to the previous iterate xn. So we just look along the line xn plus 1 equals to xn, and we look at the intersections of this line with the map. In this case, we have the fixed point at 0, and we have another fixed point here, which we can calculate by taking this equation and setting xn equals to xn plus 1. So we would have a fixed point, say x star, is equal to mu x star 1 minus x star. And so I think we get mu x star minus mu x star squared minus x star is equal to 0. So we would solve this quadratic and we would get the two different roots, and those would be the fixed points. I guess another feature to note is the symmetry in the line xn is equal to half. So yeah, we start with some point, say here, and another point here, where this distance is the same. Then it's going to map to the same xn plus 1. I shouldn't have picked this because it looks like a fixed point, but it doesn't matter too much. Yep, so the point is you go up to the curve of your map f, and then you go across to find the value it maps to. In this case, as I said, they'll both map to the same value. And if you wanted to, say, find the where it maps to after two mappings, after two steps, then from here we would reflect back in the line xn plus 1 is equal to xn. We're going to go back here, follow this back down. So it's kind of like if this was x0, then this is x1, which means this is also x1. And so now we're mapping x1 to something, so we should stop when it gets to the line, the curve f of xn, and then go back across. So this will be x2, and so on. And we would continue this same process. I mean, if you wanted to find a third one, we'd go down here, so this is x2, and then we'd go back up to the curve, and then go across. So this is x3. Yeah, so I think you get the point of, how to find the, f of something, given this map. Next, we're going to look at the tent map. So the tent map is defined as shown. Again, we can notice there's a symmetry in the line xn is equal to half, and similarly, we will say that mu is usually between 0 and 2, so that we do not leave the interval x in 0, 1. Yeah, again, looking at the line xn plus 1 equals to xn, we see that there are two fixed points, one at 0 and one here, which we can calculate, again, by setting xn plus 1 equals to xn in this system of equations. And just as a quick example, I'll show what happens if we start with some x0 here. We're going to find x1, so we go up here, we go across. This is x1. If I want to find the next thing, I'm going to reflect in this line. We go down here, so this is x1, and then we follow up to the curve f, we go across, and so this is x2. So yeah, same thing. Next we'll move on to the rotation map. So this is xn plus 1 equals to xn plus omega mod 1. And it looks like this. So yeah, as you would expect, right? This thing, the curve has gradient 1, because the coefficient of xn is 1, and because we're doing mod 1, when we get up to 1, we're going to go back to 0 again, and so, yeah, the map looks like this. We might also notice that because the gradient is 1, the curve is kind of parallel to the line xn plus 1 equals to xn, so we're either going to have no FPs, or if omega is equal to 0, then everything is an FP, which is obvious because if omega is 0, then xn plus 1 equals to xn. So everything is a fixed point. So two things to notice. If omega is rational, we have periodic motion. And if omega is not irrational, then we have aperiodic motion. Well, yeah, I think that should be quite obvious because if it's rational, then because of the properties of modulus, we're going to loop back to the same point. And if it's irrational, then we're not going to loop back to the same point. You might say that if omega is irrational and we have a periodic motion, that the forward orbit of any point is going to, I think it's going to be dense in the interval 0, 1. So in other words, we're going to cover like we can name any number, any real number in the range 0, 1, and the forward orbit of omega should hit that at some point. I believe. I could be wrong. Okay, so we'll look at the sawtooth map, also known as the Bernoulli shift map next. We'll see why it's called Bernoulli shift. But the reason it's called sawtooth is because, well, it has this shape that looks like a sawtooth. Quite self-explanatory. It's defined to be xn plus 1 equals to 2xn mod 1. And so we have one fixed point. And the reason I say one fixed point is because we're at mod 1, xn equals to 1 here is the same fixed point as xn equals to 0. So yeah, exactly one fixed point. The way that we can, justify that this can be viewed as a shift map is we write xn as a binary decimal expansion. Because it's in the interval 0, 1, it's going to be of this form, clearly with the units digit being 0. And if we multiply by 2, since we're in binary, we're just shifting over to the left by 1 place value. And because we're taking mod 1, we're going to chop off this thing that we've just shifted over past the decimal point. So yeah, it's like a shift and truncation. So yeah, we can see this is a shift map acting on binary numbers. Through this representation, excuse my spelling here, we can get a bit of intuition on what the map does. So for different starting points. So if we start with something of this form, say x0 is equal to some, finite decimal representation in binary, or you can write it as some number p times 2 to the minus n, then, well, clearly after n iterations, because we've shifted it n times over, we're going to arrive at the fixed point 0. So yeah, the solution hits 0 after n steps. Or you could just say, yeah, for like general n, the solution is just going to hit 0 like eventually, right? If we start with a point x naught, which is rational, so we can express it as some p over q, with q not equal to 2 to the n, because otherwise we would have this previous case and hit 0. Then there exists a k in the natural numbers such that after k iterations of the map, we will get back to x naught, right? Because it's a rational number, if we, keep adding to it by the properties of modulus again, number theory, I'm not going to quote the exact result, we will end up at the same number. So basically the solution becomes periodic eventually. We can think of this as, if number's rational, say in base 10, also applies to binary, the sequence of digits is going to recur at some point down the decimal expansion. And so when we get to that recurring point, we're going to keep shifting it, and say the decimal expansion recurs as a sequence that recurs after say 5 digits, then it's going to have, a periodic solution with period 5. And the last thing is, if x naught is not rational, then the solution is aperiodic, and I think that's quite obvious. The digits don't repeat in a pattern, and so, we're not going to return to the same x naught. In the next video, we're going to use this map as a prototype for chaos. Just something nice to note for next time. I think finally we have the Baker's map, which is actually a map on 2D points. So instead of before where we had, some mu, which is a parameter, and xn, which is just in 1D, we're now going to have a point with xn and yn, so just in R2, and we're going to define xn plus 1 to be 2xn mod 1, so that's basically the sawtooth map. But we also define yn plus 1 in this way. An easier way to, you could draw out the diagram for this, but I think a nice way to understand it is using this diagram of what happens in a map. And this also explains why it's called the Baker's map. So if we start with some point in, this 1 by 1 square in R2, and we label points in xn less than half to be the area A, and xn greater than a half to be the area B. So remember that to find yn plus 1, we're mapping points based on whether they fall into region A or region B. So that's why we've labelled them. Basically what this map does is we stretch this and then we squash it so that, you get this shape. So basically we've stretched it by a factor of 2 in the horizontal direction, and we've squashed it, in half, or stretched by a factor of half in the other direction, the y direction. So we get this, and then we, imagine we cut along this dotted line and we stack them together, like so. So that's what the map is doing. And that's why it's called the Baker's map, I guess, because it's kind of like you're stretching, chopping, and stacking dough. Cool, so that's all for this quick video, and in the next video, like I mentioned, we're going to talk about chaos and use the sawtooth map as a prototype for this. Great.